Hello everyone, welcome to A plus BI. This channel is all about complex numbers, and in this video we're going to be solving a rational equation, a very nice equation with complex numbers. We have 1 plus I divided by 1 minus I, and then that is raised to the power z, and the answer equals 1. So we're gonna try to solve for z. You're probably thinking, hey, there's a very obvious solution. Let's not talk about it yet, but you've probably seen it, and don't tell anyone if you got it, okay? So we're going to solve this problem in two different ways. Let's start with the first method. The first method, even though second method is usually shorter and for most people it's better, it also teaches you something, hopefully. Okay? This is an experience. And by the way, if you're new to complex numbers, go ahead and check out my lecture videos. I also have another channel, which is called Cybermath, cyber with an S, where I do algebra and number theory problems and thinking about a geometry problem, which takes me forever, by the way. Anyways, so to solve this problem, here's my first approach. I'm going to go ahead and raise the numerator and the denominator separately to the power z. Can we do that? I mean, we can do this with real numbers, but can we also do this with complex numbers? Does it matter if z is a complex number or real? Something to think about. But I did it. Too bad. Too late. I already did it. And then I'm going to cross multiply. Obviously, I don't want 1 minus I to the power z to be 0, but that can only happen if I equals 1. And as you know, I does not equal 1, right? Is it? I squared equals negative 1. That's the only thing we know. Or you can write I as also the square root of negative 1. Some people define it that way using the principal square root definition. Okay? That's why we say the square root. Otherwise, a complex number has two square roots. So negative 1 has two square roots, I and negative I. Make sense? Okay. Great. Now, let's go ahead and cross multiply. So that's going to give us 1 plus I to the power z equals 1 minus I to the power z. Great. So there's a couple things you can do about this. First, I'm going to show you the polar approach, and then we're going to go ahead and use a different approach, which I think is a little better. So it's kind of like a 1a and 1b. Oh, I should have done the 2a and 2b so I can say 2b or not 2b. But anyways, you get the idea. I already said it. Now, how do you write a complex number in polar form? Again, I go over these in the lecture notes, and we've done quite a few problems. But in the complex plane, which is called usually the argand plane, or argand plane, is the D silent, something like that, we basically express them as a point or a... In the argand plane, we basically express complex numbers as a point or a vector. For example, 1 plus I would be considered like 1 comma 1. I was going to say 1 comma 0, but that's not the case. 1 comma 1. So it's going to look like this. Okay? 1 unit here and I units here. And then, of course, this number, this point represents the number. And then you can kind of think about two things here. The distance from 0, which is root 2 by the Pythagorean theorem, and the angle, which is pi over 4. So there's two things. Any complex number can be written as r e to the I theta. R is the modulus or the absolute value, or theta is the argument or the angle. So 1 plus I, its modulus is root 2, and the angle it makes is pi over 4. So we're going to write it like this. Similarly, 1 minus I can be written like this. But this time, you kind of have to use negative pi over 4 because it's going to be in the fourth quadrant. Make sense? It's going to be right here. Cool. Same idea, but it's just a negative angle. This is better. Obviously, you could also use 7 pi over 4, but we want to use the negative sign. Okay? Cool. Let's go ahead and raise both sides to the power z so we can kind of see what is going on. This should be raised to the power z, and the other number. Notice that they're not equal, right? I mean, these numbers are not equal, but their zth powers are equal, whatever that means. And from here, you can immediately see that, okay, I'm going to have root 2 to the power z and e to the power I z pi over 4. And then this one is going to give me root 2 to the power z e to the power negative I z pi over 4, right? Something like that. These two are going to cancel out, given that they're not 0. They're never 0, right? And then we're going to proceed with this. Now, at this point, if you say, oh, okay, they're equal, iz pi over 4 equals negative iz pi over 4, then you're going to run into a lot of trouble because you're going to be saying something like, okay, pi over 4 equals negative pi over 4. That's not true. Why is that happening though? Because we do have the following interesting scenario. We could basically just introduce a new factor. How? You can multiply both sides by e to the power 2 pi ni, or just multiply one side by that because this is 1 in the complex world. So this is the complexification of 1. If you think about it in the argon plane, you're going to see what I'm talking about. But that's 1. So I can multiply by that, and by adding the exponents, I'm going to be getting a nicer equation, which the one that has hopefully a solution. And now at this point, let's go ahead and divide both sides by I pi, because I and I pi is a common factor. That's going to give us z divided by 4 equals negative z divided by 4 plus 2n. Okay, I was like 2 pi n? No, 2n. And n is an integer, by the way. I forgot to say it, but you probably guessed it, because when we say 2 pi n, we're talking about multiples of 2 pi, integer multiples. Great. Let's add negative z over 4. That gives us z over 2 equals 2n, and z equals 4n. How nice. So if n is an integer, z equals 4n is a solution. What is that supposed to mean? It means that if n is equal to 0, z is equal to 0. You probably knew that it was a solution at the beginning, which I didn't say, right? Because, come on, something to the power, oops, I didn't write an n, I was a z, right? Something to the power z is 1, that means z can be 0, because this anything to the power 0 is 1. Even 0 to the power 0, right? You don't believe that? Go ahead and check out my video that I made about 0 to the power 0 right here, so you can be hopefully convinced, and if not, then let's argue in the comment section down below, okay? All right, cool. So this means that any multiple of 4 will be a solution, but we still have the second method. Why did this happen? We did a lot of, Eulerian work. Thanks to Euler, he gave us these beautiful identities and formulas. But why did we come up with something like this? Let's go ahead and take a second look. This is the second method, okay? Obviously, the second method is usually nicer, but again, it's up to you to decide. So what am I going to do with the second method that is different? I will simplify inside the parentheses first, which is usually a good idea, because why would you deal with a fraction, right? Or a rational expression? Why don't we simplify this? And what is that equal to? You can multiply by the conjugate of the denominator, which is 1 plus I. I keep saying conjugate, but that's the verb, to conjugate, but it's the conjugate. And we get 1 plus I squared. You should definitely know that 1 plus I squared is 2i. Okay, memorize it. And this is from sum of two squares, 2. So the answer is I. How nice. So this whole thing, which is in disguise, right, is 1. So I to the power what number equals 1? The answer is, well, we know that I to the 4th is 1, but I to the 8th is also 1, because this is I to the 4th to the 2. So any power n here will do. So z equals 4n is actually a legitimate solution. And that brings us to Wolfram Alpha, right? Ta-da! And Wolfram Alpha can solve this problem. Good job, Wolfram Alpha. We'll give you credit whenever it's due, okay? And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.